So the Arrhenius equation, I like to call it the Arrhenius equation because it helps me to remember how to spell it. And the information given here is relevant for OCR Chemistry A specification. Now, if you think back to your first year rates, so when you increase the temperature, what happens to the rate of reaction? Okay, so think back, the rate increases. But can you remember why? Why does a rate increase? And it's to do with the Boltzmann distribution. So the Boltzmann distribution, remember, just shows the spread of energy in the molecules. And as the temperature increases, the Boltzmann distribution shifts to the right at a higher temperature. And that means that more molecules have got energy greater than the activation energy. So you should be able to recall that from the first year rates. And also, when you increase the temperature, the particles are moving faster and they collide more frequently. So just hold those two things in your mind initially, and we'll come back to them in a second. So the Arrhenius equation is an equation linking rate constant with activation energy. And there it is. And you've got your rate constant, which my handwriting is not very good. It's meant to be a lowercase k. You've got the pre-exponential factor or the frequency factor, and that is effectively constant. And then you've got the part of the equation called the exponential factor. Going back to what we talked about a moment ago, what affects the rate of reaction, then it is number one that has the greater effect, the larger effect. Number two is more minor, the particles colliding, moving faster and colliding. So it's actually number one that has the greater effect. And this part of the Arrhenius equation, that is due to the factor number one, that the more molecules have got energy greater than the activation energy, and then this part here is due to number two, the frequency of collisions, that they're going to collide more frequently. And number one has the greater effect, the larger effect on the rate. Okay, now do you need to remember these equations? Do you need to remember them? No, they are given on the data sheet. And also the natural log version, LNK, that's given on the data sheet as well. So you don't need to remember them, you just have to be able to use them. So if we look at the LNK, which is actually the most useful here to use, if we just slightly pull away the 1 over temperature, can you see the relationship with a straight line, y equals mx plus c, and the LNK is the y, the 1 over temperature is the x, and then you're going to have the gradient of the line being minus EA over R. So if you plot 1 over temperature as the x-axis, and remember the temperature has to be in kelvins, that's a capital K, and then the y-axis is the ln K, natural log K. Make sure you're pressing the right button on your calculator, because it's not the log button, it's the ln button. Okay, and then you plot, and then when you get the line crosses the y-axis, then that's going to be the y-intercept, and that's going to be c, and the gradient of the line is m. But you've got to be careful when you're calculating this, because the gas constant R is in joules per mole per Kelvin. So therefore you need to divide by 1000 to give the activation energy in kilojoules per mole. The activation energy needs to be in kilojoules per mole. So to work out the activation energy, you just need gradient times R divided by 1000. And this exam question, a multiple choice question, this is taken from the June 2019 OCR Chemistry A H43201 paper. And let's see if you can work out the answer. So maybe you want to pause the video for a second and have a go work out the answer yourself. Okay, so we have been given the gradient, and you have to find the activation energy. Okay, so I hope you've already worked out the answer. So the gradient is minus 4420, and we can cancel out the two negative charges. We rearrange the equations as the gradient times R, the gas constant. Don't forget to divide by 1000 as well to bring the units to be kilojoules per mole, and your answer is 36.7 kilojoules per mole. Thank you. Goodbye.